Excellent. So today we're going to be presenting on the advantages of optimization-driven design. And in the webinar itself, we'll be going over the philosophy and the value optimization-driven design, including applications and examples. So we're excited to have you and look forward to the discussions that come out of it. A couple of housekeeping points for you. First and foremost, this will be an interactive webinar where we will have short polling questions throughout. So we look forward to your input and your answers. That's going to help spur some of the discussion and conversation as we move along. However, if you have questions as we're going through the material, please don't hesitate to reach out and ask. There is a question feature as part of the GoToWebinar tool. And so as you add your questions, we'll aim to address them towards the end of the webinar, or even by email if we run out of time. Please also note the presentation material will be shared by email, and we'll also be sending over a recording of the presentation. So in terms of who's talking and who's here, first and foremost, my name is Daniel Mazar, and I'll be your host for this webinar. In terms of my role, I'm responsible for customer success and sales operations for Maya HTC, an engineering firm that I'll be introducing shortly. Joining me is Martin Gambling, Managing Director of GRM Consulting, who are the developers of OptiAssist for SimCenter 3D. Martin has worked in the field of design optimization and structural analysis for over 20 years, working in many different industries. His aim in optimization is always to make it relevant to day-to-day engineering development, where it can really make an impact. And we wholeheartedly agree with that. So we're happy to have you here and bringing our expertise and leveraging our engineering backgrounds and the work we do with different customers to help solve your business and engineering challenges. Quick note, this webinar is hosted by Maya HTT, as I mentioned, organization I work for. Maya is a leading provider of digital engineering solutions and the #1 global partner for Siemens Digital Industry Software. Our history started off in aerospace and working on thermal and flow simulation, but we've really expanded out to help in multiple different areas and industries and complex engineering challenges over the last 3 decades. With offices in US, Canada, and UK, and operations across the globe, we're happy to help customers regardless of location, as long as there's engineering problems to be solved. Today, we'll be covering just a small subset of what we do, as I had mentioned, in terms of optimization and the work with GRM, but our expertise ranges quite a bit beyond simulation, as you can see here. I won't get into too much detail on each of these different areas, but if there's problems or issues in relation to product lifecycle management, industrial IoT, AI applications, manufacturing, these are all areas where we're seeing some tremendous growth in terms of challenges coming up for our customers. So I think AI, for example, being able to go ahead and capture data related to a part in the field or in quality assurance as part of the engineering workflow, and then turning that into valuable information or supporting further when it rolls out towards an optimization type problem. These are all areas that we're able to help out with quite a bit. So there's quite a bit more we can talk about, but really we wanted to bring back our focus to today and the work we're doing with optimization. So with that, I'm going to go ahead and pass it over to Martin, who's going to bring us through the agenda and the presentation. Martin, off to you.
Wonderful. Thanks, Dan. Hopefully you can all hear me. I guess Dan will soon let me know if that's not the case. So good morning to all of you guys. It's just the afternoon over here where I am, but delighted to be presenting to you all. So as Dan said, I'm going to be talking about the agenda you see in front of you here, which is, first of all, discussing the philosophy of optimization-driven design, what it means and how it can help in your day-to-day developments. And then I'll go into the detail of OptiAssist for SimCenter 3D, the product that enables that philosophy inside SimCenter and NX. And then we'll look at some of the specific applications and some examples of those and how it can be applied and has been applied already. And then we'll have a little wrap up and I'll return to Dan to catch some Q&As at the end. Okay, so first of all, optimization-driven design. What is it? And what do we believe it offers as a process? So really, optimization-driven design is that process of bringing structural optimization methods into the day-to-day analysis. So some people in the audience may have already be using optimization or familiar with it. And I guess the key thing here is that rather than optimization sitting as something that is a separate step, something at the very start or an action at the end of a development to see if you can make some improvements, it's used to guide design right the way through the development process, saving a lot of effort and time for the engineer as it does so. And the key thing with it, when we do it right, is we can solve for multiple requirements, which most products have these days. And we can use it to resolve design issues as they occur through that development process. So you can see here, it can be applied across the whole stage, early concept, which may be topological, through developing architectures, and even down to detailed component developments. Okay, so let's first take a look in terms of the process about how we do things now. And this is making the assumption that we're working in an FEA-based iterative design scheme. So designs are released and they're incorporated into analysis. We're performing our simulation and providing that feedback back to design and developing our products that way. So when we do that, we can follow the flow that you see there on the right, which is to perform your finite element analysis, take a look at the results, assess your performance against the targets that you have set out. And then really you take a look and you make a decision as a design group, an engineering group, is this good enough? Have I met my targets? Do I think there's room for more improvement? If there is, we stop. If there isn't, that's where we use our experience and some of our engineering calculations to make a design change. And then we go through the cycle of updating the design, either directly in the FEA or back to design. And then we go through this loop of manual iteration, updating models and developing. So if we take a look at optimization-driven design, it really is not so different. And that's the key thing, I think, to consider when we look at how we can apply it in our development cycle. So in terms of the steps you see in manual design, we review performance. Well, here in optimization, we're setting ourselves goals or objectives, and we're also setting constraints on the optimization that we must meet. And then we, as engineers, go, is it good enough? Okay, if it is, great, we stop. If it isn't, we carry on. That's what the optimizer sees as convergence. And then in terms of knowing how to change the design, that's where engineering experience can come in, and the optimizer is calculating design sensitivities, which is the change in how your part or your design is going to change with respect to the different developments you can make to that design. And then we perform our optimization and we revise our design. And so when we look at that flow, it's the same that engineering process that we're doing, but what we're really doing is just leveraging the fact that there are tools that can save us time, both in terms of elapsed time and engineer time making these changes. The updating the design can become automated, the review of the targets, again, automated. And so we have this optimization-driven philosophy of how we design and develop. And there's some real key advantages too in terms of the process. So by having the tools considering these multiple requirements, so we can have stiffness and strength and vibration in an optimization, we can consider those multiple requirements really efficiently. Traditionally, if we're doing something through iteration, quite often we'll fix one design issue, maybe something's not stiff enough, and we'll maybe add some material for that. And then we'll repeat the same process for the vibration or the stress limit, and cumulatively adding material each time. And really with optimizers, we can get that solution that develops the best compromise to manage all the different requirements. And then in terms of time savings, that automatic update really is a key one. So why should we use it? Hopefully some of these answers are already becoming self-evident. But the key thing is, when we're using it right, we can deliver better designs faster, and making the best of the available design processes and manufacturing processes we have. So a good example really is the thickness distribution of castings, and we'll see that in an example shortly. A key one for me personally, something I've worked using optimization for many years, is saving iteration time. If I can look at a part and I've got maybe 50 different panels and I want to change their thickness, I don't want to spend my time iterating through that thickness change to find out the best combination. Let's let an optimizer do that for me. I can go off and do something more useful. I can do other engineering activities, or I can get a coffee. It's fine. I'm happy. As mentioned, we can also look at identifying those designs that meet the multiple requirements. So we're putting in targets for stiffness and for stress and vibration, and getting that best compromised design across the different requirements. And then through optimizing parts, the bit that is more typically understood and considered as an advantage for optimization is minimizing your part cost and your material usage. So this inherently is something we're all driven to do in engineering design these days. So making the best use of the materials and the technologies we have is really key. And then lastly, something actually some of our current customers are really taking advantage of is using optimization to rapidly assess the feasibility of different design concepts. When you're able to automatically optimize a concept to a solution through optimization, that means you can generate a few different schemes, different concepts, and see which one ends up presenting you with the final best solution in terms of mass or performance. And we'll see that in one of the last examples we'll go through, which is something done by INEOS Team UK, one of our UK customers who is using optimization-driven design through OptiAssist at each stage of their America's Cup yacht development process. Okay, so Dan, over to you, I think now for the first of our poll questions.
Excellent. Thank you, Martin. Great introduction already. So I'm going to go ahead and put up the first poll question, which should launch in your windows shortly. And I'll just read the question so it's clear. So do you use SimCenter 3D, previously known as NXCAE, and SimCenter Nastran for your structural analyses? Please select one. Yes, we use SimCenter 3D and Nastran for all our FEA. Second, yes, we use SimCenter 3D and Nastran for some of our FEA. Or third, no, we do not currently use SimCenter 3D or Nastran. Go ahead and give you all a few minutes to answer that. Great. Just another 15 seconds or so, and then we'll be ready to move on. All right. Thank you all. I'm going to go ahead and close and just share the poll. So this is good to know. It sounds like the majority of you have some form of SimCenter 3D and Nastran in relation to your FEA. 17% is using SimCenter and Nastran for all, 44% using it for some, and 39% not using it at all. So I think it's helpful for us to understand as Martin gets into the next section of the presentation where we'll be talking a little bit more about the tool. So Martin, with that, I'm just going to go ahead and pass it back to you.
Great, thanks, Dan. Wonderful. Yeah, actually, just for me, I've hosted many webinars over the years, but that's the first time I've had poll engagement. So thanks for doing that, Dan. It's really helpful just to know what the audience are using and sort of pitch the explanation of the next part of the presentation, as it were. So on to the next topic, which is talking about OptiAssist for SimCenter 3D. So good to hear there's a good percentage that are already working in the SimCenter environment. For those that aren't, hopefully the rest will still become very clear in terms of the applications and the features. So first of all, I guess, what's the objective of OptiAssist for SimCenter 3D, the product I'm just going to introduce you to now. And the real aim is to develop this single unified environment that allows you to maximize the potential of what's actually already inside Nastran, this optimization module known as Sol 200. And OptiAssist achieves this in two ways. It first of all provides a really easy and engineering-driven interface to optimization for each of the trails that we will see through the remainder of the presentation. And secondly, it adds additional capabilities. So some that you may or may not already be familiar with in terms of what's out there in the market. It's making sure that these tools are available inside SimCenter 3D. And so really as a product, it's an enabler for this philosophy of optimization-driven design, and it's embedded in the tool where you are doing your day-to-day analysis and your design. So it all brings that together. So in terms of the methods that are available, we've got 5 that I shall work through here, and you can see first of all we have a process that's known as bead optimization, or also described as topography optimization. And this process allows you to automatically develop form in shell structures, and that form can be evolved to maximize the stiffness of the part, just for static stiffness or for dynamic performance, or even for relieving stress peaks. You can just smooth out the geometry automatically to develop that best form. It's really useful because it doesn't require any additional mass. It's just moving the shape of your part around, so adding features that you can design in. Secondly, we've got gauge optimization, which is also known as sizing optimization. And this is one of my favorites for just saving me time. As mentioned, if you've got a lot of panels, a classic example is an automotive car body. In such an example, you don't want to have to sit there iterating the panels. So if you can set the different requirements into one optimization, OptiAssist and Nastran can simply guide you to the best distribution of thicknesses. And we can extend that into a little bit more control and flexibility of the thickness distributions for parts such as castings or moldings, whereby we have flexibility in the manufacturing for the thickness distribution, so we can use the optimizer to automatically subdivide our part up and optimize the thickness distribution for that multiple requirements. We then have free shape optimization, which is really refinement of an existing design. So if you've got something, you maybe have developed it through topology first, or it's just your existing design, you can let the optimizer just move the surfaces in and out a small amount to refine your design's geometry to increase stiffness or remove some mass as required. And then lastly, we've got the topic of composites. It sort of sits there on its own in a way. This is an area that either you're fully engaged in, you're working in the field of composites, or it's not relevant to you. If it is, optimization for composites is really a very strong capability, because composites have that flexibility of tailoring stiffness and strength in different directions. Having a tool that can tell you where those plies should be placed and at what orientation and the shape of those plies is really important, I think, and something a particular speciality of mine is working in that field, and really you can take advantage of it really well. So I've got just a quick introduction video to it so we can see OptiAssist in action. You saw the 5 areas you see there, and the key thing you can see is that it sits inside SimCenter 3D, and we've got this setup trail that remains common for all the different methods of optimization we're going to apply. You can see here how the results of a gauge optimization are presented, and we can easily compare the improvement in stiffness we achieve. What you see on screen now is the animation just going through the histories of the optimizer's iteration. So it's where it's working its way to a solution of the thickness distribution of this example. And again, you can see here a clear comparison two parts that essentially weigh the same with a great deal of improvement in their characteristics. That stool that you just saw then and this boot floor from a car body are two examples we'll go through in a bit more detail shortly, so you can see how it works and the kind of benefits you can achieve through optimization. And then lastly, on the metallics side of things, we've got FreeShape, where you can see just with a more of a nice test case to visually show what's happening, how we can tailor that thickness of a design. As we move into composites, you can see here we can start to interrogate the placement of different fibers, ply fibers, their orientation and the material types, as long with the total thickness. Its application in Formula One is something that's become really quite mature over probably close to 15 years. And also, I think more recently, it's expanding its usage into aerospace and other arenas, such as marine, as we'll also discuss. Okay, straight away, we're back to poll question number 2, Dan, so I'll hand you back. Okay.
Great, thanks. I really appreciated the introduction there on OptiAssist and within SimCenter 3D itself and the different applications. So we're going to go ahead and launch the second poll at this point, and I'll just read it. Feel free to start answering. First and foremost, are you already using some type of optimization software product? Please select one of the following. Yes, we use a structural FEA-based optimization solver. Second, yes, we use a general purpose MDO optimizer, examples such as HEADS. Thirdly, no, we do not currently use any optimization software. So please take another 30 seconds or so, given your answers. Again, this will help us in terms of tailoring the next portion of this presentation. Perfect. We'll give it another 15 seconds or so. All right. Thank you all. I'm going to go ahead and close the poll at this point and share the results there. So in terms of what we have, 37% of you saying yes, you've used some form of a structural FEA-based optimization solver, 16% using a general purpose MDO optimizer, and 47% not using any optimization software. So I'll say in my experience, I would see that when it comes to sort of organizations that are leading in terms of their industry or are doing more innovative stuff, the number skews a bit higher in terms of using some kind of optimization software, or even if you're not having some software, just having it as part of the engineering workflow. So definitely an area to explore. Martin, I don't know if you had any thoughts as I pass this over to you in terms of what you're seeing in the poll compared to what you see out in the field.
Yeah, I think that's a fairly good spread, a typical spread of what we see in industry. As you mentioned there, because obviously our company, our business is very much involved in optimization. What we do, we're already working. We know the industries and the sort of teams of people that are have adopted already optimization, and often some of the body optimization, automotive, motorsport very heavily, and I think anything where there's that need for performance improvement is often a lead-in. But I think what we see more and more is the requirement for part cost reduction, material usage, and so on. That's where it really offers something that we're seeing that bigger growth into the wider world, as it were.
Yeah, great insight. And I think this next section, as you get into application examples, may jog or stir up a couple more ideas. So I'll pass it back to you.
Wonderful. Okay, great. So yeah, hopefully this is the sort of a bit more interesting bit now, digging into the details of the methods and some of the applications that we've done, our customers have done, and so you can really sort of see the sort of benefits and processes in place. And so we'll put at least one example for each of the different methods as we go through. So first of all, if we look at thickness optimization, so this would be your sizing, your gauge optimization, or also what we would call free sizing optimization. And for this process here, with gauge, it's taking each individual panel where, from a manufacturing point of view, it must be the same thickness, but we can change the individual panel thicknesses. And then on the free sizing, when the manufacturing process allows you to have that flexibility of thickness, well, we can take advantage of that and let the optimizer develop those thicknesses. So hopefully you can see it's quite key that the methods align to the manufacturing process that you're designing for. So if we take a look at this example we have now, it's not the most glamorous of paths, but actually it really is a powerful example of how the process works. It's a kitchen stool, so it's made of injection molded plastic, where we do have that flexibility of thickness distribution. And the design here, designed as a uniform 3mm molded part, you can see it's exceeding the material limits at around about close to 50 megapascals of stress against a target of 20, and displacements are close to 9mm, where really we want to be less than 5. So how can we develop that thickness distribution in an optimal fashion, saving a lot of iterations, and work out our solution? So when we use OptiAssist for this, we would set a rule to change the thickness from 2.5 to 8mm, what we consider sensible for our manufacturing. And then we utilize the automatic subdivision rule. So we just say, hey, I can split by feature angle. As you can see, the colors that you're seeing on screen are separate, denoting the different thickness zones that have been automatically generated. And we just go and optimize the part against our targets for stress and displacement. And so you can see here, here's our result. We've now got a part that has that variation in thickness. We have added some mass over the original design, 140 grams, but you can see the stress has gone down from 49 megapascals down to below the target of 20. Displacements have similarly reduced by almost half down to our target, and it's that really small mass increase. But I think that's the key. It's a key example here about optimization-driven design is often used where somebody spent the time developing something, and then they go at the end, can I optimize it? And what we're trying to say here is this is just bypassing the need for that manual iteration. It's saving that engineer time. So this development is part of the normal development cycle. It's very much how we work. This is the way we just free up our engineers, let the computer do the thinking, and get that material distribution directly from the optimization. And what you get at the end of this is an FE model that is the optimized thickness. So you have that design at the end that you can look at, you can interrogate, you can analyze further in FEA as if you were doing it without optimization. It still sits in that same process. So now we'll look at a second approach, this bead optimization, where we're putting swaging patterns into a form. And hopefully this is actually one of the tutorial examples when you're getting started with OptiAssist, and you can see the form developing through the iterations. This very simple example is just maximizing the natural frequency of a square plate. So you can see how it's formed swaging patterns in that plate to get the solution we want. And you can see the natural frequency, it's gone up from 2000 to almost 3000, no mass change. And so that's all automatically managed. So when we look at how we see that being applied in the real world, and this is something that is used if you're working with pressed parts, it really is a key enabler for just making life easier, really. If we take a look at this boot floor, challenge here was to try and get some weight out and actually improve the design. So here we've got the loading in the trunk. I should say in Britain it's boot, with you guys it's trunk, so apologies for the different terms. But really what we want to do is develop a revised beading pattern in that floor part to make it stiffer, reduce the stresses, and ideally be able to down gauge the material. And so actually what we've done with the form that you're seeing evolving, the contour that's animating is the depressions, the swaging patterns in the boot floor. With that, you can see we're able to reduce the displacement by really quite a significant amount, down by 65%, reduce the stress by 24%. And because of that, we've managed to do all that whilst also reducing the gauge of that floor panel from 1.2 millimeters down to 0.9 millimeters. So that's a 25% reduction. And that provides not just a reduction in the mass of the part, but also when you've got a thinner part you're stamping, there's lower pressures in the tool, so you can look for cheaper alternatives to production. So it has significant benefits along the way. And the key thing is, it's just that simple modification to that existing design process. So we're not trying to revolutionize anything, we're just using optimization in how we normally develop and taking advantage of it in the right way. So next, we've got the application of free shape optimization. And this is really not so different to what you saw in topography. The difference here is we're doing that movement of the mesh automatically, but we're doing it on the surface of a solid part. And Optisys does this by moving the surface nodes. It's also going to be moving the internal loads to smooth out to keep good quality in your mesh. And here in this particular example, we just wanted to make things stiffer. This is a 3D printed upright motorsport application, and we didn't want to make any change in mass, but can we make things stiffer? And so we've just simply told the optimizer, hey, you can move the surfaces inwards by a mil, just shave a millimeter off the surface where you can, and you can move material outwards by 3 millimeters anywhere you see fit. And you can see here stiffnesses, of which there's components in terms of vertical, lateral, and braking stiffness. They were all increased by 15%, and that's with no change to the mass. So again, it's just you set it up, you hit go, you go home, have your dinner, and the next morning you've got the result that you can then interrogate as an updated FEA model in your simulation. Okay. So now we'll move into the area of composites. I thought it important to have a great big section header for this one because the area of composites is very different to the other aspects that we discuss. And there are two real processes that are available to you through the optimization-driven design philosophy of composites. First of all, we can look at ply shape development. So if we take the example here of a Formula One chassis, the approach that's taken is to cover your composite structure with a uniform laminate to start with. So you'll have what we call candidate plies. So here we'll have 0 degree and 45 degree cloth plies. So these are the woven plies that you see in composite structures. Then we've also got unidirectional fibers oriented at 0, so along the length of the chassis, and 90 going across the chassis. So these are the angles and the materials we want to consider and understand where we should best place them, and equally how many we should place. So there's a lot of detail that we can go into in this area, but we'll just overview it as part of today's presentation. And the key thing here you can see is the contour on screen now is a thickness contour of the unidirectional fibers that should be placed on your chassis. And this is again meeting many load cases. So I think this particular example has 3 stiffness cases and around about 11 strength cases that we're trying to meet. And here you can see this red area is the thickest area of where it wants to place unidirectional fibers along the opening of the cockpit. And again, that you can see there's a lot of sense in why it wants that to strengthen the part. If we look at the placement of 90 degree plies, these are then sitting around the front and the headrest area in the cockpit aperture, and then at the rear where it's mounting to the engine. And then lastly, we can see where we can place 45 degree woven plies. These are really good for carrying that shear stiffness, and that's managing all the torsional stiffness of the chassis. So you can see that's more of a distributed thickness that we see. And within the process, there are tools to just automatically recover your ply shapes. So these thickness contours get converted back to recovered ply shapes. And as you mature your design, you can provide much more control over those divisions of the ply shapes, so you get something that's quite easily manufacturable. So the second example or the second process, I should say, is to optimize an existing laminate. Sometimes the nature of where you are in the development cycle is you don't want to change your preforms, your shapes of your plies. So what you're going to do is just simply understand if by adding one of a certain ply, you can take two of another out. Is there a better combination of plies and their orientation? And so you can do that. And again, this is all fully hooked up inside SimCenter to the Laminate Composites module, so you can optimize directly from it and update your laminate back. So in terms of that laminate optimization, why is it so important? And this is actually one of the really key strengths of optimizations in this area of composites, is you can consider those many different requirements. Again, that is across the board with all optimization. But in the area of composites, you can really maximize the potential of the composite material. So you can work with its inherent flexibility and ability to tailor stiffness and strength in different directions. So that works well. And the key thing, engineers also do a good job. We mustn't lose sight that engineers have got good experience, good practical considerations of realistic things that need to be considered in design. So part of the process is making sure the tools have the ability to let the engineer feed those manufacturing factors in, and we believe that it does that. But the other area as well is if you're into a new area such as composites and you don't already have that experience, well, the optimization is going to start to guide you and inform you and educate you on where plies should be placed and how they should best work. So just a couple of examples on composites, and I think we're pretty much wrapped up, making sure we're keeping good time in the webinar today. And one quite recent example, this is within the last 12 months, we've been engaged with an OEM, hypercar OEM. It's so recent we can't say who it is. So I thought I'd share a picture of lots of hypercars, all the ones I'd love to say are in my garage and very definitely aren't. But in terms of the process here, this was I just jumped aside there, Dan. This was a process whereby they were in quite a lot of trouble in terms of their development program. They were almost 40 kilos over budget in their chassis, and they needed to resolve that. So they engaged optimization to solve that issue, and they did it in two stages. They used that ply shape process that I've described in a more of a free way, a little like you saw on the chassis, to understand the best layout of plies, to manage all the different requirements. And these are vehicle crash for maintain the strength of the chassis, torsional stiffness, vibration, attachment point stiffness. So many requirements were considered. And then once they understood that layout, they redeveloped the ply shape optimization, putting in realistic zones of where they could actually subdivide the plies. So introducing that manufacturing constraint. And through doing that, they were able to achieve a real tangible reduction of 39 kilos in the chassis, and it really brought them back from a difficult situation to being back on track as a vehicle development program. So a real win for them. Okay, and the second example, I touched upon it at the start of the presentation, is Ineos Team UK. So these guys are really pushing the limits, and I don't know if anybody listening has ever seen these America's Cup boats sailing, but they're pretty extreme the way they foil above the water. And so they've got some tough load cases to manage there, and so they're using optimization at every level. So globally, they'll look at the hull layout, the ply distribution, all the placement of the unidirectional fibers to meet all the whole global stiffnesses. And then the way they see it is they just use it at every level. So it's sub-assemblies, so bulkheads, they'll look at tape placement, right down to simple components where just rather than spending a day iterating a part, they spend an hour optimizing the thickness of a component with that confidence that it is the best thickness distribution. And we asked them, because there's actually a more detailed presentation on all the work that Ineos have done. If people would like that to be made available, they presented at the SimCenter conference last year. And I asked them what are the real benefits they saw. And the key thing is they don't have to have preconceived ideas for their ply boundaries or for their thicknesses in their parts. They can let the optimizer guide them to the best solution, and that allows them to rapidly look at different schemes. So in their case, they've got maybe different hull concepts for the flow through the water, more efficient designs or not. And so they can rapidly evaluate those and see what the implications of different flow concepts are in terms of the resulting structure. And that just lets them design things more quickly. So, okay. So that's going through some examples. Dan, it's back to you for the final poll question.
Wonderful. I'm going to go ahead and get that set up. While I do, Martin, we have seen some questions start to trickle in, so you may want to just start taking a look at those as well. In the meantime, I'm going to go ahead and launch this one and walk everyone through this. So, what are the primary manufacturing methods used for your products and designs? So please select all the ones that are applicable. We have stamping / pressing, casting or forging, injection molding, machining, or 3D printing. So again, we'll give everyone about 30 seconds to go ahead and start answering, giving their insight. While they're doing that, just a couple of comments on my end, Martin. I really appreciated the examples you were showing. I think it's great to just see how we can boil these back to tangible benefits, right, with hard numbers. And on top of that, the fact that when we're able to look at the optimization problem and being able to do it in multiple ways, right? Like the INEOS example there. And by the way, for those that would like more information, INEOS example, please just leave us a note as part of the chat, and then we'll be sure to include it as part of our outreach. But just going back to, global sub-assembly level, component level, all those different areas, I just really liked, I think, the level of detail we got into there. So I appreciated that.
Hey, no problem at all. I have to be conscious I don't talk too long. I find myself easily talking too much, so hopefully I've not got on too much for all of you guys today.
When it's great stuff, then it's helpful. All right, I'm going to go ahead and close the poll. Just quickly share the results. And Martin, I'll just pass it off to you if you have any comments on this. But yeah, we're looking at 21% stamping, pressing, 29% casting or forging, 50% injection molding, 57% machining, and 21% 3D printing. So you may have a comment in terms of what you're seeing in terms of these methods with some of the customers you're working with. But I'm going to go ahead and get the presentation rolling for you at the same time.
Great. Okay, thanks. Yeah, I think actually just seeing that poll is quite interesting because often I think additive manufacturing, 3D printing is something that's really elevated optimization just on a general level, and it is a really fast growing and a significant new, or not even so new, but newly expanding area of manufacturing. But it's important looking at the other methods there. There was a lot of injection molding in there, a lot of castings and forgings, and that's actually, as well as the 3D printing, where we see the application in the areas of casting thickness that we've been working on. This is a process that I've been working with companies in die castings for, sadly it shows my age, probably close to 18 years in terms of the thickness distribution and optimizing for that. So it's actually hopefully reassuring to people out there. It's not always new technology. It's just making sure that it's used in the best way and it's accessible in the way that you want to design and develop it. Optimization shouldn't be a hardship to do. It should be easing your working tool. Okay, so just one more slide from me, really, just to summarize what I feel and what we believe optimization-driven design offers. And really the key thing is trying to avoid that, getting stuck in that unpredictable loop of design iterations. You get to a performance, I'm not there. Okay, I'll try something else. I'll try something else. It may work, it may not. And engineers are great problem solvers anyway. So we've all found our ways to get there. But if there's a tool that can really ease that journey for you and give you that guidance to what's feasible much more quickly, then I think that's really what optimization-driven design offers. And you can use it to look at trade-off studies of designs and fix those design issues. And that's a really key thing. And in all of those areas, both composites, as we say down the bottom, and all other areas of manufacturing, you can use it for those multiple requirements, and that just really makes things easier. Okay, so Dan, I think that wraps up my presentation. Thanks everybody for listening there. I've got some time now for some questions, which I think I can't see them, Dan. So when they come through to you, they'll be very much live for me to answer.
just the way we like it, putting you on the spot. No, I'm kidding. We'll go for it. So we have one here. Is it possible to prioritize certain load cases above another, weight factors, etc.? For example.
Yeah. So the way we've configured OptiAssist is to be as straightforward for the everyday as possible. So you say, it'll ask you what your goal is. Are you trying to make it minimize mass? Are you trying to maximize stiffness? And it will focus on one. But you've got an option just to click an advanced button, and then you can start to build up combined targets. So you can say, hey, I want to maximize stiffness and maximize frequency. And you can, with each of those, you can place weighting factors to give that bias. So yeah, that's quite straightforward.
Perfect. Next one, and this one's very specific to OptiAssist, so I'll chuck this to you. Since it's based on SOL 200, I'm assuming that OptiAssist can work on FEA model-related parameters, i.e. mesh, properties, etc., for the optimization, but not the CAD model, as in model parameters, sketch dimensions, etc. Is that correct?
That is correct. Yeah, that's been well understood there. Clearly, whoever's asked that knows their stuff. So this is an FEA based optimization route. What we do have in the current version is the ability to update your FEM, so be it thickness, be it shape, or laminate, whatever you're working with. There's direct updates to the FEM, so you can create just a new duplicate or overwrite your current FEM with that optimized result. Part of what our developments and on our roadmap are very much to bring that back into the CAD, though. That's a real driver for us, because we understand people want that in the design side afterwards. So we're already working with Siemens directly on this, on the best ways to get that back. Sometimes it's a little more tricky than we'd like, because people design in different ways. So updating somebody's design model when they're designing it in different approaches is something to take a little bit of care of. But no, so well understood, and that's how it currently works.
Yeah, well, good question, good answer. And again, if there was optimization related to the CAD model, you need the most support, just send us a note and we can set up a follow-up conversation there. Great. I have two more questions for you, Martin. One is it possible to have synthetic constraints, equation-based, for example, when it comes to optimization through OptiAssist?
Yeah, so that's a good deep question, whoever's asked that one. Yeah, so I assume that's something like the ability to have some sort of relative displacement, because typically we'll go minimize mass, we've got displacement constraint, but actually you've got to make a relative displacement between 2 points, or some calculation of a stiffness based upon the loads and maybe several points that are moving. And yeah, that's possible to set that up, so you can manage that in the optimization, no problem.
Perfect. And final one for now. And again, if you have more, feel free to ask and we'll go over by email. I just want to be mindful of time. If we're looking to add optimization as part of our engineering workflow, where should we start?
I would say probably talk to us or the team at Maya in terms of what you're doing. And I think part of the key to adopting optimization right is for somebody who is experienced on it to get an understanding and appreciation of how you're currently working. I don't want to create any sort of scariness about optimization, but there are so many tales of people just taking it, having a go, using it in the current process, getting it wrong, then running out of time because they've done it in the time they were going to do it manually, then getting a bit scared and going back. So making sure that we can say, hey, this is actually the approach that suits you and would work best for you, and pose the questions right. And then that can go through straightforward training of the products with follow-up application of it. So I would say is the key.
Perfect. Excellent answer. And I would agree. I think in terms of where to get started on that journey, let's have a conversation, help you identify really what's the problem and the objective, and then work you through it with our expertise on the tools. Wonderful. That was excellent, Martin. Really appreciated that. So just to wrap it up, we know we have a couple more minutes here in terms of what we have, in terms of what's next. I'm just getting a little excited. So we touched on this a little bit, but as I mentioned, we're going to go ahead and share the recorded presentation at the end of this. So that'll be coming your way if you want to forward it to more colleagues or you need to have more of a conversation. We'll also have a short review survey for you. It's just going to help us ensuring that future webinars and material will be tailored towards what you're liking. So if you could take the 2 minutes to fill that out, we'd really appreciate it. Second, and this goes into the question we had on, where do we start? As a thank you for attending the webinar, staying the whole time and going through the material, we're actually offering a complimentary engineering assessment for the attendees of the webinar. So if you're interested in that, what this means is we start off with just a 30-minute conversation on just discovering where optimization may be a good fit, or even if it's a good fit for your workflow. If you're interested in that, just send an email over to info@mayahtt.com, and you can reference the webinar and say, I'm emailing for my complimentary assessment, and someone will follow up with you accordingly. Thirdly, as mentioned in the beginning, there's a lot more webinars that we have in place that are going on, especially in this time where a lot of people are working from home or remotely. We want to ensure that you have material, and this is a good time for you to be able to jog some ideas and really just think about how to better optimize the work that you're doing. So just keep an eye on that, and you can find that on our website on mayahtt.com/events. All right, a couple more points for you. So we also have a trivia challenge that's going out, and we know how much engineers like sharing facts, and just curiosity is really part of the role. But we have a live trivia challenge going on right now on engineering facts all over the place. You basically can go ahead and go to mayahtt.com/trivia. You're playing for bragging rights, and there's also prize money and over $500 available. I believe you get 2 minutes to answer as many questions, and you get up to 3 tries. And there's a large pool of questions, so I don't think they're going to be coming back again. But for any of you like me who have that competitive spirit, or would just like to, maybe take a quick coffee break to challenge yourselves or have a little bit of fun, do check it out. It is the Ingenious Trivia Challenge. Yes, we can spell. Yes, we like wordplay. So go ahead and check that out as well. We're looking forward to you enjoying that. And with that, we are at the end of the webinar. Again, thank you so much for staying. We'll follow up with the remaining material, and we wish you all have a great day and a great week ahead. Thank you so much, Martin, for all your help as well. I think
no problem. Thank you all.
Presentation.
All the best. Take care.
Bye now.